Now that we've laid a groundwork for multivariable equations by looking at linear equations, I want to look at systems of equations. Now, a system of equations is a set or a group of equations where the variables in however many equations you have represent the same quantities in each equation. So, for instance, if we have the system of equations 3x plus 4y equals 10, and 4x plus 8y equals 12, we have x and y in both of these equations, and this x are the same, and this y and this y are the same. And so you have essentially two pieces of information about these variables instead of one. And the general rule is that with systems of equations, if you have the same number of equations as you have variables, you can solve for values for the variables. You'll recall with a single two-variable equation, we couldn't solve for values for x and y. We could only solve for those variables in terms of the other variable. So with a system of equations, if we have the same number of equations as variables, generally we can solve for values for those variables. Now there are two exceptions to that rule. One is if the two equations are contradictory. So for instance, if you had the system of equations x plus y equals 5 and x plus y equals 1. These two equations are contradictory because they're telling you that the same quantity, x plus y, is equal to two different things. And this obviously can't be solved for values. The other situation where you can't solve for values is if the two equations are redundant. So, for instance, if we have x plus y equals 2 and 2x plus 2y equals 4. These two equations are redundant because they tell us the exact same thing. If we divide each term in this second equation by 2, what we're left with is equation 1. And so it's really no better than having just one equation. We can't solve it for the values for these two variables. One way to think about solving systems of equations, at least linear equations like this, is to think about it graphically. The definition of what we're looking for here can be shown very easily on a graph. Let's say that this first line, the graph looks like this, and this second line, the graph looks like this. And we have some x and y axis here. Let's say this is x and this is y. And this point right here is where these two lines intersect. And so this point has an x coordinate and a y coordinate. And the values of this x and y coordinate are the values for x and y that satisfy both of these equations. And so that's how you can kind of think about systems of equations graphically. And in this case here where we have the contradictory equations, this would essentially be parallel lines. The equations x plus y equals 5 and x plus y equals 1 would look something like this. You'd have these two parallel lines that never intersect. And so that's why you can't solve these for either variable. And in this case, with the redundant equations, this is as though you have one line drawn on top of another line. And so the solution for this is the entire line. So in both of these cases, there's no way to solve for x and y. But if you have the same number of equations as variables, and they're not contradictory and they're not redundant, you should be able to find what is graphically the intersection point and solve for values for the variables. In the next couple of videos, I'm going to demonstrate a couple of different methods for solving systems of equations.
If you need a study guide, click the book at the bottom of the page. If you want more free test videos, subscribe to us on YouTube. If you just want to keep watching, click the next video.